Our next presenter is Paul Vinik with GPI. He's going to be talking about the success of two 30-year-old cathodic protection systems.
Good morning. I'm Paul Vinik, and it's a privilege to be here. Thank you for this opportunity. I'm going to discuss the two 30-year-old cathodic protection systems installed in Florida. So first, where are they? The Crescent Beach Bascule is just south of Jacksonville. It traverses the Intercoastal Waterway and is within a few hundred yards of the Atlantic Ocean. The Howard Franklin Bridge traverses Tampa Bay, which is an estuary of the Gulf of Mexico. And just point out, Florida has 1,350 miles of coastline, more than any other state except Alaska. So these two cathodic protection systems are in service. They're protecting a double-leaf bascule and a major interstate highway. On the left, you've got the Crescent Beach Bridge, aerial picture. State Route 206, double-leaf bascule, half-mile long, one lane each direction, about 12,000 AADT, and 7% of that trucks. And it opened to traffic in 1975. The Howard Franklin is Interstate 275 over Tampa Bay. It's a fixed bridge. It's about 3 miles long. It's a major interstate artery between Tampa and St. Petersburg. AADT is 178,000 per day, and about 5% of that is truck traffic. And it opened to traffic in 1960. So the focal points this morning will be the technology and the science. You know, how does CP work? The design, how do we implement CP? The construction, taking us from the drawings to the real life, and then the maintenance and the economics of the two bridges. So first of all, the technology and science, and just real simple terms, everything that can be observed has a native voltage that can be measured. A potential is the difference between two objects and is the driving force in a corrosion cell. So reference electrodes provide an established baseline and are used to quantify corrosion measurements. So we've got the setup of what's commonly used up here. We've got a high impedance voltage meter. We've got a copper sulfate reference electrode on a wet sponge. We've got our rebar encased in concrete, and we make a connection to the rebar on the positive side and the reference electrode on the other, and we read the potential between the concrete and the steel. ASTM C876 gives us a probability table based on that potential that we can use as a general idea of whether corrosion's taking place or not. Energy flows downhill, right? Energy will flow from a high energy material to a low energy material. This is a fundamental principle in corrosion and is also, by the way, the second law of thermodynamics. This is illustrated using the very common zinc anode connected electrically with steel. If they're unconnected electrically, both the zinc and steel samples will release electrons to the environment and both will corrode. However, if they're wired together, the higher energy zinc electrode at a native potential of minus 1.2 volts will flow electrons to the steel, which has a native potential of about a half a volt. So energy is flowing downhill. We've taken advantage of the higher energy zinc alloy and the second law of thermodynamics to protect the steel from corrosion. When electrons flow from an alloy or from a metal, that's what creates corrosion. The metal oxidizes. That's an example of a galvanic system. An impressed current system is the same exact principle, except that the electron flow is provided by a DC power source. At the bottom here, I just wanted to show that all of this can be represented with an electrical circuit, including capacitances and resistances. So how do we apply this in a bridge structure? Let's start with a galvanic pile jacket system, which mitigates corrosion in the tidal zone. Why is that important? Because the tidal zone is the most severe area where corrosion occurs. We've got abundant oxygen and continual wet and dry periods. We wire the steel reinforcement to a zinc anode, expanded wire mesh. Below the waterline, we install bulk zinc anodes. By embedding a reference electrode in the grout and wiring the components into an accessible junction box, we can monitor the performance of the system by measuring the potential between the grout and the steel reinforcement. And while the materials differ, these same principles can be applied to caps, piers, and bridge decks. So what do we've got? We've got our monitoring station We've got the red line here going to a reference electrode. We've got our steel cage. We've got our concrete. We've got our zinc mesh anode and a polymeric jacket around. So it's really pretty basic. So first, let's look at the Crescent Beach Bridge. It opened to traffic in 1975. You can see that by 1986, the use of low-density concrete, not enough cover, poor construction, all resulted in significant substructure spalling and degradation after only 11 years of service. I say we. I spent quite a bit of time at FDOT. I slip every now and then. FDOT rehabilitated these elements by removing the bad concrete, installing additional reinforcement, installing a CP system, and then encasing it with new concrete. And this is what the design drawing looked like. We've got conduits, we've got our negative junction box, we've got a 3-inch gunite layer, we've got negative and reference electrode wires, here's our anode mesh and our current distribution bar, our negative junction box, we've got our concrete spacers, our new concrete footing jacket, we've got our negative connections to the footing reinforcement, we've got access ports, our embedded reference electrodes right here, and so on. We won't go through the whole drawing, but this is what the design for the repair of that footer looked like. So the Crescent Beach pier caps received an impressed current cathodic protection system. The existing concrete was repaired. A titanium mesh anode was installed along with additional reinforcement to restore the structural integrity. The pier footing picture still needs to be formed, but is almost ready for placement of the new concrete. And in the picture, it's a little bit blurry, but you can see behind the reinforcement that there's the titanium mesh has already been installed. The picture on the left is of an off-the-shelf pile jacket fitted by the manufacturer with spacers that create an annular space for the grout, a zinc anode expanded wire mesh, and it is pre-wired for easy connection to a junction box for system monitoring. I want to point out, these are just off-the-shelf jackets. Once the jacket's installed, it's fully filled with cementitious grout. The picture on the right is of an installed jacket that once the wiring is finished will be complete. The bottom of the jacket should remain submerged, and the top of the jacket is traditionally about 6 feet above high water. So the pile jacket protects the pile in the splash zone. We've got a 50-pound bulk anode submerged and wired up into the junction box, and we can add additional reinforcement if we need to restore capacity. Here's some more rehabilitation work at Crescent Beach. The picture on the left shows completed pile jackets and a bent cap cathodic protection systems. The picture on the right depicts the channel excavated in the bent cap for the titanium ribbon anodes. Some more construction pictures showing the struts and columns that are being prepared for impressed current systems. On the left, we have the concrete repairs are complete, the titanium mesh anode's been installed, and it's being held in place with Christmas tree fasteners right here. You can see them in the picture. So they're holding the mesh tight to the concrete. The L-bars have been dowed into the existing concrete as well. On the right, the titanium mesh anode is in place. The GFRP L-bars are in place and tied to the newly placed reinforcement. Both of these are getting close to placement of new concrete. In total, what was repaired at Crescent Beach? What was the extent of the repairs? FDOT did 45 galvanic CP pile jackets, 14 impressed current CP systems on bent caps, 4 piers, including impressed current CP systems on columns, footings, and struts. The impressed current CP systems have embedded reference electrodes and cellular telemetry for remote monitoring. Well, how much did all this cost? That's the money rules everything, right? So in 1988, FDOT installed impressed current cathodic protection systems. They encapsulated CP with encapsulation, and I apologize, these are quick notes out of FDOT spreadsheets, so the grammar and language isn't necessarily the best, but they rehabbed 8 footers with severe structural damage, and CP was installed in addition to the structural repairs. It cost $15.40 a square foot for a total of about $46,000 in 1988. Going through, we've got some concrete repairs, spot paint, and install CP on 21 piles, a cost of $500,000 in 2017. And in 2018, just recently, cathodic protection integral pile jackets, non-structural, a cost of about $3.3 million for a total cumulative value of $3.9 million over the decades from 1980s into the 2020s. Now let's look at the Howard Franklin Bridge. The pictures depict the condition of the substructure in 1988 after 23 years of service. And just like Crescent Beach Bridge, the construction with low durability concrete, not enough cover, and exposure to highly corrosive environment led to significant early life corrosion and substructure degradation. FDOT chose cathodic protection preservation rather than demolition and replacement. And again, like Crescent Beach, it is in full load service today. I'm not going to go through all of the construction and repair techniques with this bridge since it's all similar and analogous to Crescent Beach. The installation of cathodic protection systems on the Howard Franklin began in the early 90s. Additional repairs and CP systems have been installed over the decades. This is a screenshot of the telemetry system utilized to monitor the effectiveness of the CP systems. The on and off potentials can be compared for each channel, and the output voltage and current from each rectifier is provided. The data is available online, along with weather conditions. Some bridges in Florida have depth gauges to monitor scour and flooding conditions, as well as laser sensors to detect movement. But that's kind of ancillary to this presentation. But I do want to point out we've got 92 channels here, each representing a different CP system. Let's see where we're at here. Let's look at channel 77. We've got bent 171, and the output voltage on the rectifier is 1.6 volts. Channel 78, we've got the output current at 1.1 amps. Again, at bent 171, we've got an on potential of minus 0.6 volts and an off potential of, well, this one's reading the same 0.62, but here we've got the different on and off potentials at each channel that can be compared and monitored to evaluate the performance of these CP systems. So now let's look at the cost and repairs and maintenance. And the next slides contain the contract values let to repair the Howard Franklin from the late 1980s until present day. We're starting out 1987. We installed impressed current cathodic protection, gunite encapsulation of the CP with remote monitoring. It was at $25 a square foot for $400,000. Yeah. So we won't go through all these numbers, but let's hit a couple of the big ones. We've got 1992, we installed galvanic cathodic protection, sacrificial zinc, bulk zinc anodes, as we showed in the pile jacket schematic, rehabbed approximately 62 piles. About 2,000 square feet of concrete was protected, and the cost per square foot includes the cost of additional bulk anodes per pile plus the zinc sheet anode, about $42 a square foot for a sum of about $1.5 million. Some metallizing in 2001, about 40,000 square feet of metallizing at about $32, a $1.3 million investment. Again, I'm not going to go through them all, but you can see here in 2004, $1.4 million, 2006, another $1 million, 2009, about $2 million. Bit of investment, right? Throwing a lot of money at this bridge. But 2009, another $1 million, sacrificial cathodic protection pile jackets, 96 piles protected. More work, galvanic again in 2011. But this is, I think, where the rubber hits the road. The contract to build the new Howard Franklin Bridge was a record $814 million. That's the reference. I like to keep it simple. You know, I haven't included any user costs, no traffic control costs in this, no predictions. It's just kind of simple and common sense math. But by utilizing cathodic protection, FDOT was able to extend the service life of the old Howard Franklin Bridge by 34 years. If the new structure makes it 75 years without any additional repair costs, it will have cost the taxpayers of Florida approximately $10 million a year. So what I've done, I've taken this 814 and said, I like it easy. I'm going to say it's $750 million. It's a 75-year design life. Cutting that down linearly, that's $10 million a year investment from the taxpayers of Florida to construct the new Howard Franklin Bridge. The cathodic protection system took us from 1990 to 2024, which is the predicted opening of the new bridge. That's 34 years. If I take that times $10 million a year of service life in today's money, that's $340 million. If you look at it that way, which I'll readily admit isn't necessarily exactly accurate, but it does put things in perspective, that the CP systems paid for half of the new bridge. So extended service life, it just makes sense. From 1988 through 2016, a total of 21 contracts were let to repair the substructure components of the Howard Franklin, summing to a value of $15 million. Several of the contracts included in this estimate are known to also include repairs to other bridges in the district. For this reason, the estimated total cost is knowingly higher than reality. They're driving piles for the new bridge in the bottom picture, and again, I can't say it, that CP saved the $325 million. The calculation shown is representative and provides a perspective when comparing the cost of properly performed preservation with the cost of new construction. So I'd like to share two excerpts from research conducted into the use of cathodic protection to protect bridges. NCHRP Synthesis 398 on the left concludes that state highway agencies have experienced a reduction in the frequency and cost of bridge maintenance and an increase in service life. The Federal Highway publication on the right concludes that cathodic protection is the only rehabilitation technique that has been proven to stop corrosion. I didn't feel I could leave this presentation without providing the bridge inspection reports. Here's the report for the Howard Franklin from 1991 through 2018. I couldn't find the newer reports. Maybe I need to get with Jeff. But as you can see, in 1991, the substructure of the Howard Franklin was rated poor with a sufficiency rating of 41. CP systems were being installed. The substructure condition is improved and actually outperformed the superstructure in certain inspections. Here's the analogous report for Crescent Beach. Again, we've got the substructure in satisfactory condition through fair, starting in 1991 through 2018. Now, 2018 is when the big contract was let to repair the Crescent Beach Bridge. So substructure repairs have maintained the condition of both of these bridges and kept them in full service for 30 years. To me, that's pretty impressive. There is training available in this area for cathodic protection that's specific to concrete structures. And if anybody's interested in getting their personnel some specific training in this area, I'll be glad to point them in the right direction. AMP offers the corrosion and protection of concrete structures courses, and it's a 3-day course with written and practical exams. FDOT had a big say-so in the practical exam for this course. And here's a picture I stole from Ivan, but if you don't preserve your structures, your bridge is going to close, someday, sometime. Are there any questions? And thank you very much. It's my privilege to present to you guys. Some of the systems used, metallizing, for instance, Dick, it's not a long-term, decade type of repair. So FDOT knows going in when they use metallizing, if it's close to the water line, certain conditions, you're going to get an 8 to 10 year type service life. So yes, some of those metallized areas had to be remetallized, and some of the other conduits and things with the CP systems were repaired in some of those contracts. Yes, we were trying to preserve the structure as long as we could. The Howard Franklin was rated deficient, and they were considering demolition and rebuilding way back in the 90s. And the cathodic protection systems have gotten us to today.
All right, thanks again.
Thank you. I left my thumb drive, is it?
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.